All right, on this first problem, to evaluate the limit, start by taking 9 and plugging in for x. Take note of how you get 0 over 0 back. From here, what we want to do is we want to apply L'Hopital's rule. In applying the rule, we continue to take the limit as x approaches 9. We take the derivative of the numerator. In the numerator, we have x to the 1/2, so the derivative would be 1/2 x to the negative 1/2. Negative 3 here would go to 0. We place that derivative over the derivative in the denominator. Derivative of the denominator would simply be 1 for this x, and then 9 would go to 0. If we simplify this a little bit, we have the limit as x approaches 9. Since we just have a 1 on the bottom, really all that we have to do here is clean up the top. So as we clean up the top, we've got a fraction. It's going to be 1 over 2. This negative exponent will bump down to join that 2, making this x to the 1/2. At this point, now that we've applied the rule, we want to take 9, we want to plug in for x. When we plug in for x, we've got 1 over 2 times, this is technically the square root of x, so it's the square root of 9. It's 1 over 2 times the square root of 9. Square root of 9, of course, is 3, so it's 1 over 2 times 3. We get 1/6 back. And problem number 2. We start the same way as we did in the previous problem. Take 3, plug in for x. Take note of how you get 0 over 0 back. Because of this, we continue to apply our limit. And we apply L'Hopital's rule by taking the derivative of the numerator. Derivative of the numerator would be 3x squared minus 8. And we place that over the derivative of the denominator, which in this case is just going to be 1. So at this point, we're ready to plug in 3 for x. We have 3 times 3 squared minus 8. 3 times 3 squared, well, 3 squared is 9, times 3 is 27. 27 minus 8 will give me 19 back. Moving on to number 3. For number 3, we start the same way. We take 0, we plug in 4x. Now we've got some trig stuff to work with here. So recall from the unit circle, since x is approaching 0, we'll focus our attention at this point on the circle. At that point, we know the x-coordinate is 1, the y-coordinate is 0. So if we're inserting 0 in for x, we have 6 times 0 here, which is 0. The cosine of 0 would go with the x value at this point, so that'd be 1. 1 minus 1 gets 0 on top. Obviously, plug 0 in the bottom, we're going to have 0 down there, so we have another indeterminate value. Because of that, we can apply L'Hopital's rule. We continue to apply the limit as x approaches 0. In applying L'Hopital's rule, we take the derivative of the numerator, so 1 would go to 0. This negative will get applied to the derivative of the cosine of 6x. The derivative of the cosine of 6x, well, I'll start with the cosine. Derivative would be negative sine. We're taking the negative sine of the argument 6x. But then remember, you have to tack on the derivative of that argument, the 6x part, so that derivative would be 6. There's our derivative for the numerator. Derivative of the denominator would be, since that's 3x squared, 6x. Now, at this stage, I could do some reducing, but if I don't do any reducing and I simply plug in 0 for x, well, 0 for x goes in here. You have 6 times 0, which is 0. If you're taking the negative sign of 0, let's see, sign goes with the y value, so the y value at this point would be 0. All of this becomes 0, meaning everything else as I multiply it together would be 0 over, replace x with 0 down here, this would also be 0. We get another indeterminate value. That means we have to apply L'Hopital's rule again. So as we apply L'Hopital's rule again, we take the derivative of the numerator again. Now, let's clean this up a little bit. We know these two negatives would cancel to make that positive. This 6 is being multiplied onto the trig function, so that can just kind of come along for the ride. As I continue to apply the limit here, because I'm continuing to apply the rule, I have the limit as x approaches 0. This 6 I'm going to move to the front, and I'm going to multiply that to the derivative of the sine of 6x. The derivative of the sine of 6x would be cosine of 6x times 6. And that is all over the derivative of the denominator, which would simply be 6 at this point. Once again, I could do some reducing. If I don't do any reducing, though, and I just simply plug 0 in for x, 0 goes in for x here. I have 6 times 0, which is 0. The cosine of 0, as we've talked about before, is 1. So all of this would become a 1 when I apply the limit, meaning I have 6 times 1 times 6 all over 6. 36 over 6 would give me 6 back as my value for this limit. Okay, to use a linearization here on number 14 to approximate the cube root of 8.05, what we need to start by doing is we need to start by establishing a function. So f of x will represent our function. Since we're talking about a cube root of 8.05, we'll use the cube root of x. We also need to establish an x value here to play with. The x value we're going to choose will be 8, because 8 is the closest perfect cube to 8.05. Now, doing the linearization, we start by finding a point. To get that point, we simply take what our x value is of 8, and we plug into our function here. When we plug in 8 to our function, we get the cube root of 8, which of course is 2, meaning our point will be an x-coordinate of 8, and then the 2 we got back from plugging into the function. For our slope, to find the slope, we have to take the derivative of the function we've defined here. So f prime of x is going to equal, since this is equivalent to x to the 1/3, we bring down 1/3. We have x to the negative 2/3 left if we subtract 1 away from that 1/3 power. As we simplify this derivative, because I have this fraction and this negative exponent, I set up a big fraction here. Denominator would include a 3 because of the denominator from this fraction. It would also include an x to the 2/3 power, because I'm going to bump this guy downstairs, and when I bump it downstairs, the negative goes to a positive power. All that remains on top would be a 1. So now moving on, since I have a simplified form for my derivative, I'm going to find the slope. To find the slope, I'm going to take my x value of 8, I'm going to plug in. So I'm going to have 1 over, it'd be 3 times, okay, understand with the fractional exponent. Denominator here, this means I'm taking the cube root of this value. So it'd be the cube root of 8. Numerator means I'm squaring that. So I have 1 over, cube root of 8 is 2, 2 squared is 4, times 3, just follow my order of operations here, I get 1/12 back for the slope. Now normally at this point we move on to an equation, but understanding the equation would be the next step, and after that we would have the linearization. Let's think about what the equation would be, and let's cut straight to the linearization. Linearization. L of x. Well, that's going to equal our slope of 1/12 times the x minus the x value at our point, which was 8. And then normally we have point slope form, where over on this side it'd be y minus our y value, which is 2. So if this is going to be y minus 2, and we're just solving for y here to get L of x, we'd be adding 2 over. So there's my linearization function. Using my linearization function, I can now evaluate the cube root of 8.05 by taking 8.05 and plugging in to this function I've come up with. When I plug in 8.05 to this function, rounding off to 3 decimal places, I get 2.004. right, now if we look at number 15 here, we're trying to approximate the same value as what we were playing with here in 14, only we're going to use the differentials approach. To use the differentials approach, let's start in the same manner as we did on 14. Let's establish a function. Let's let y equal, in this case, the cube root of x. Once again, we're using the cube root of x because I'm talking about a cube root right here. Let's pick out an x value to use that would be logical. Once again, we're going to choose 8 because 8 is the closest perfect cube to 8.05. But now using this differentials approach, we need to establish a dx. Well, dx will simply be the difference between the value I have under the cube root I'm trying to figure out up here minus this closest perfect cube of 8. That differential will be 0.05. So now using the differentials approach, we take the derivative of this function we've set up here. Because we're using differentials, we use dy dx notation. Since we've already done this in the previous problem and we know what it simplifies to 1 over 3 times x to the 2/3, let's go ahead and use that here. Now, what you want to do at this point is solve for dy. When you solve for dy, you multiply both sides by dx. So the dx swings over to the other side. And at this point, we are now ready to plug in for some variables. One variable we're plugging in for is x. We know x is 8. So we have 1 over the 3 times. Remember how this fractional exponent works again. It's the cube root of 8, whatever that is, squared. Squeeze that in there. We're multiplying that to dx. The dx we found was 0.05. We remember from the previous problem how this broke down. This comes out to be 1/12 when we calculate everything. So it's 1/12 times 0.05. Calculate that out, that value comes out to be 0.004. So at this point, we're ready to draw a conclusion. We're ready to conclude that our approximate value for the cube root of 8.05 is equal to, well, at this stage what we do, we understand the cube root of 8.05 is going to be really close to the cube root of 8. So it's going to be within the proximity of 2. We're going to take 2 and we're going to add on this differential for y we found, of 0.004. When we add those together, we find our approximation is going to be 2.004. That should make sense because that matches up with our linearization answer we found in the above problem.